Just a few words about Edward. He is a researcher at Berkeley after having studied at Yale, MIT, and Bell Labs. He's been a software engineer and systems engineer and researcher for 40 years now. He's very much interested into cyber physical systems. And of course, the integration of computing and the physical world, as the title of this keynote indicates it. I think Edward has delivered a book entitled The Entwined Futures of Human and Machines. And I guess the presentation we have today will have very much to do with the book. Edward, if you are ready, I think it's up to you now.
Okay, thanks very much. I really appreciate the invitation. I lead kind of a dual life these days. Most of the time, I actually am a hardcore engineer. I work on software for cyber physical systems. I've been working actually on software for cyber physical systems for about 40 years, long before there was ever such a term. 40 years ago, in the 1970s, I was writing assembly code to control robots in a clinical pathology lab. So it was an industrial automation application. But these days, I lead a bit more of a dual life where I spend some of my time on more technology and society issues. And it started with a project where I wrote my first book, which is this one, Plato and the Nerd, which came out about 3 years ago in 2017. It's the subtitle is A Creative Partnership of Humans and Technology. It was an attempt to kind of reach out to a broader audience and to write a book like what is commonly done in the scientific community, but much less done in the engineering community, which is a book that really steps back and looks at our discipline. And I think I was not completely successful because I was unable to keep technology out of it enough. So there's quite a bit of technical content in it. My latest book, which is the Coevolution, which forms the basis for this particular talk. I actually, when Eric and Shahram approached me to give this talk, I thought they wanted me to talk about my work in cyber physical systems because it's a very good match to the conference. But no, they insisted. They really wanted this talk that is more focused on technology and society. And I said, well, I mean, I actually don't like promoting my books, but I've made a public commitment to donate all of the royalties from this book to the Wikimedia Foundation, which is the organization behind Wikipedia. So I actually don't mind promoting the book because I think Wikimedia Foundation is a fantastic organization. And so, if I can get you all to buy it, that will help one of my favorite organizations. Getting you to read it might be a different story, but in any case, I'm going to give you a little bit of an overview of the content of this book, and hopefully it'll be thought-provoking, and it is very relevant to the conference, and so I hope that it'll generate some discussion. Okay. So the context that we're in today is extraordinary, of course. We're turning into digital humans all of a sudden. All of our interactions are mediated through screens these days. I personally relish giving talks in front of live human beings, and it's rather difficult for me to do this in staring at my screen. I have to keep reminding myself that there's actually all of you out there. And this is an image of a group meeting that I had just last week. This is my research group. And a lot of things have changed. I mean, one of the things is that my research group is now scattered around the world, as is this conference. It's almost 1:30 in the morning right now here. So if I sound a little sleepy, that's my excuse. But we're all learning how to do this, and there are some benefits and some obvious disadvantages to this, and I think we're adapting. And the key thing that I'd like to emphasize is that actually the technology and its relationship with humans right now is going through an enormous transformation that's forced by this pandemic. And the theme of this talk is on coevolution of humans and technology. And one of the interesting things about evolutionary processes, biological evolutionary processes, things that I learned while I was researching this book is I used to think that they were rather slow and gradual processes, but apparently they're not really. They're more like punctuated equilibriums where there's major disruptions that happen in an ecosystem that force significant transformations in the entities in the ecosystem. And I think we're seeing that now with technology and the relationship between humans and technology, where things are changing over the course of just weeks in ways that will actually stick with us for a long time. I think the graduation ceremony that was held at Berkeley just a couple of weeks ago was kind of an amazing event because there's a group of about 100 students voluntarily got together and built a replica of the Berkeley campus in Minecraft, which is an online gaming system. This image shows a piece of the Berkeley campus with the main library in the foreground and the campanile in the backdrop. And you can actually wander through Minecraft and walk into these buildings. And a virtual graduation ceremony was held there. And of course, all of the participants in the graduation ceremony were these little blocky icons, avatars, which of course didn't resemble at all the humans behind them. And so that kind of conversion of people into these avatars that are blocky and jumping around is very unsatisfying. And hopefully we will learn to do things a little bit better. I think there's also, even with one-on-one digitally mediated interactions, this is a screen image from a conversation that I was having with one of my graduate students last week. And, we were intensely engaged in a technical conversation, and he was looking directly at my eyes on his screen, and I was looking directly at his eyes on my screen, but neither of us perceived the other looking into our eyes. And, this making of eye contact, in fact, I have to keep reminding myself when I give these talks that I really should be looking right at the camera, even though I have no interest in talking to the camera. I have an interest in talking to you, but I don't see you in that camera. And so that we lose this sort of natural eye contact, which is such an important part of human interaction. And maybe there's a technological solution for that. I'm not sure. So the very short summary of my talk is that we humans actually have less control than we think over technology development. I've spent 40 years writing software, and I used to think that every piece of software that I wrote was the result of conscious, deliberate decisions that I made. And so it was a creative product coming directly from my mind. And I now realize that's not actually the case, that every piece of software I've ever written is actually a mutation of some previous piece of software. And that the nature of the piece of software that I wrote was very, very heavily influenced by the whole cultural ecosystem within which I created that piece of software, the programming languages and the tools that I used and the libraries that I used. Those all had an enormous amount of effect on the outcome of my creative process, and probably a disproportionately large effect, so that actually my personal effect was really rather minor. So there's implications with this, right? One is that if we want to establish policy, right? So these days, one of the reasons that I turned to spending a fair amount of my time on technology and society issues is that I think that our discipline is growing up in the sense that we are realizing that fairly suddenly our impact on human society is much bigger than it used to be. It's enormous, right? And the threats of even very disruptive effects, the changing of the nature of work due to AI, for example, is something that many people are very scared about. The threats to democracy right now, where democracy seems to be crumbling around us in the face of technologically disseminated information. These effects are enormous, and we need to somehow learn to manage these effects. And of course, one of the classic techniques that we have is to establish policies at governmental levels and so forth. But the reality is that if we have less control than we think over technology development, then establishing these policies may be more difficult than we realize. So it's a more nuanced problem. And one of my goals in working on these books and doing this kind of research is to get conversations going so that we get a better understanding of what our relationship actually is with technology, so that we can learn how to manage it. Now, I have to emphasize right away that my book is not a doomsday book. There's a lot of books out there that you can go read that are talking about the runaway explosion of super intelligence, right? As soon as the machines develop a certain threshold of intelligence, they will be able to improve themselves. They'll be able to write their own programs, and they're going to leave humans in the dust. Okay, well, there's lots of books that you can read like that, and that's not what my book is about. My book is about actually the present. I'm not really doing much speculating at all in the future about the future. It's about what our relationship is with the technology today, and so I think that's really the emphasis. So this coevolutionary theme, the fact is that the major theme in this book is that instead of technology being the result of what I call in the book top-down intelligent design, technology comes about through a much more Darwinian kind of process, where humans are the agents of mutation. We create mutations on technology, and then in the ecosystem, there's a selection of survival of the fittest, to use Darwin's own term, a natural selection process. We tend not to think of it that way. We think of essentially a software system or a software product like Snapchat as having been designed by some brilliant designers who somehow got the design just right, so they were able to take off in the marketplace and go viral. But that's not really what happened, right? I mean, there have been over the last few years, thousands, tens of thousands of experimental software systems for social media interactions, and a few of them took off. But they didn't take off because they were head and shoulders technologically above everything else. They took off because they got lucky in an ecosystem and maybe had certain features that gave them just a slight bit of edge in a competitive ecosystem in a natural selection process. That's a very different kind of outcome than a top-down intelligent design. So a direct quote from my book that is hopefully provocative enough to entice you to read it and read my whole argument about how I defend this is that, we don't like seeing our mental cognitive processes as themselves cogs in a relentless, purposeless evolution. But is that what they are? So that's really the question that I'm addressing here. So the way that I go about addressing this question, and I'll walk you through a few of the highlights in the book. So in the first chapter, which is entitled Half a Brain, I start drawing an analogy between technological artifacts and living things. And in fact, when I was first working on the book, I started calling these technological artifacts living digital beings, which I then shortened to the acronym LDB, which I then just shortened to the word LDB. And in fact, in the earlier drafts of the book, I was using the word LDB throughout instead of machine. And the publisher didn't like that. The publisher thought the word LDB was silly and it would detract from a serious message. And so they talked me out of using that word. But I still use it in informal conversation. But the point that I make here is that if you look at a machine like this happens to be a picture of one of the Wikimedia Foundation server farms. So the Wikimedia Foundation maintains, I think it's currently 5 server farms scattered across the world, each of which has hundreds of servers in it. When you go to Wikipedia, you get directed to the closest one geographically to you, assuming it's up. If it's not up, you get directed to one that's further away. And each of these server farms has a subset of the Wikipedia database in it that is a cache, effectively, of the most commonly accessed pages in that geographic region. And my argument in this book is that this machine, which is actually distributed around the planet, has an awful lot of the features of a living being. It was born in the year 2001 on a single server. It was much smaller than it is. In fact, that server doesn't exist anymore. Much like in the human body, most of the cells in my body are not the same cells that I was born with. It's a certain percentage of them are, but an awful lot of them are just completely different cells. And the same thing is true of this Wikipedia system. And Wikipedia is, it seems like a living thing in that it's really a process. It's responding to stimulus from its environment and reacting to that stimulus. Now, of course, its growth is very much mediated by human beings. It's not growing on its own, so it doesn't quite yet have this property of autopoiesis, as it's called, of self-sustaining replication and growth. But it's the technology is starting to get to the point where we're able to see that kind of self-replication, and I'll give a few examples of this. But this idea of looking at technology as an evolution rather than a top-down intelligent design, I think I'd like to illustrate this with this picture. In fact, most of the pictures I'm showing are actually pictures in my book. This is a picture of me standing in front of Vasa, which is a ship that was commissioned by the King of Sweden in the 1600s during a war with Poland that Sweden was having. And it was a very ambitious design. And you can see 2 rows of gun decks there. It really needed to be a fairly aggressive war machine. But it was not a successful design. In fact, it was launched and sailed on a maiden voyage with about 200 people on board who were essentially partying, to celebrate the launch of this new ship. And about a kilometer off the dock into the fjord, a breeze came up, the boat heeled over a little bit, water started coming in through the lower gun decks, and the ship promptly sank. And about 30 of the 200 people on board were killed. And the ship sat at the bottom for about 300 years. And because of the low salinity and low oxygen water in the Baltic Sea, it was actually very well preserved, and it got refloated in the 1960s, and then there was a major preservation project to preserve this ship. And you can now visit it in Stockholm when we're allowed to travel again at the Vasa Museum, and I really recommend going there. It's a fascinating visit. But this ship is an engineered artifact, and a rather unsuccessful one. And I'd like to read you a quote from the French philosopher Alain, who is Émile Auguste Chartier is his real name, but he went by Alain. That was his pen name. He said, "Every boat is copied from another boat. Let's reason as follows in the manner of Darwin. It is clear that a very badly made boat will end up at the bottom after 1 or 2 voyages and thus never be copied. One could then say, with complete rigor, that it is the sea herself who fashions the boats, choosing those which function and destroying the others." So this is a Darwinian perspective on engineering. So from this same perspective, Snapchat was designed at least as much by teenagers as by the software engineers at Snap Inc. Think of it from that perspective, because it was the choice from a very competitive ecosystem of many mutant designs, mutant variations on the same concept, and it's the one that happened to succeed. So going to my favorite L2B, Wikipedia, you can say, all right, well, maybe you're stretching this too far, right? What really is life? Well, if you look up Wikipedia, look up life on Wikipedia, you'll find a page that at least at the time that I looked at it a few months ago, I didn't look at it today. Wikipedia pages can change, right? But At that time, it claimed that there was a reasonable consensus among biologists that in order to be considered a living thing, it had to have these 7 properties. So let's look at which of these properties Wikipedia has. Well, it certainly responds to its environment. Okay, it gets stimulus coming in over the internet and it responds. It certainly has cellular structure and composition. It's got those 5 server farms with hundreds of servers in each one. It certainly has growth and development, although that is very much mediated by humans. It certainly has homeostasis, which is the maintenance of stable inner conditions. It has the computer-controlled air conditioning systems in the data centers. It's got on the circuit boards, it's got temperature control as well as voltage regulators on each of the chips. These are homeostasis mechanisms that are analogous to those in biological systems. Does it have metabolism? Well, that's much more of a stretch, because a perfectly reasonable definition of metabolism is the energy-related processes in a biological cell. And if you define it that way, well, there's no biological cells involved, and therefore it doesn't have metabolism. But if you define it more broadly, as it is defined in this Wikipedia page, as deriving energy from chemical reactions, then actually that, at least in the US server farm, the energy that drives the server farm comes primarily from burning natural gas. So it is deriving energy from chemical reactions. Now, but to me, these analogies are maybe not that useful. They're sort of cute, right? And maybe give you a different way to think about a being like this. But the much more interesting ones are reproduction and heredity. So, does Wikipedia reproduce? Well, if you go to GitHub, every one of the probably millions of GitHub pages these days has a wiki. And this wiki is very much fashioned after Wikipedia, and in fact, probably shares code, has inherited pieces of code from the wiki technology behind Wikipedia. So there's a heredity of traits as well as a reproduction mechanism. And of course, there's also more primitive reproduction mechanisms in the form of things like computer viruses and the like. So I'm not the first person to draw this analogy between living things and technology. In fact, I first heard about this from Kevin Kelly, who was the founding executive director of Wired magazine and is a technical visionary. And he's given a wonderful TED talk about this. And he wrote a book called What Technology Wants. And he coined the term the technium for what he called the 7th kingdom of life. And he argued that technology of all sorts could be considered to be a living thing and evolving in much the way living things evolve. Now, Kelly included in his technological artifacts things that I wouldn't call living. They're static things like a hammer, or he focused on musical instruments. He happens to play the cornet, which is a musical instrument, and he talked about the design of the cornet as being something that got inherited, and so he was drawing the analogy that the cornet was kind of like a living thing. But to me, life is a process, not a thing. It's not, and I think this idea of life being a process and not a thing is captured very nicely by Daniel Dennett, who said, "It ain't the meat, it's the motion." And according to Douglas Hofstadter, who is actually the person I got this quote from, so it's an indirect quote. It's Douglas Hofstadter quoting Daniel Dennett. And Hofstadter says that this was a subtle hat tip to a not so subtle, clearly erotic song written in the 1950s. But the key thing is that life is a process, not a thing. And so it's not the computer that's living. It's not the server. It's not the Ethernet wires. It's the execution of the software that is the living thing. It's not even the software itself. It's the execution of the software. If the software isn't running, it's dead. If it's running, however, it is then a process, and it's that process that's interacting with its environment. By the way, I don't think it's accidental that Daniel Dennett has cultivated a beard that looks enormously like Charles Darwin's beard, because Dennett has been a very forceful advocate of understanding many of the dynamical processes around us, including cultural processes, as evolutionary processes primarily. Now, I briefly mentioned computer viruses and worms. These are among the few technological artifacts that are capable of self-reproduction. So this is a particular image from a blaster worm. So on the left of the screen, you can see the hex code dump from the blaster worm. On the right, you see the same hex code interpreted as ASCII, and there's a little message to Bill Gates hidden inside the source code here, which is kind of a curious thing about that blaster worm. But this is a piece of software that is able to replicate itself and spread itself around the world. So, and of course, we've seen various forms of artificial life explorations in software. This is a static image. I mean, I really should have a dynamic image here. There's no excuse for this, right? I mean, life is a process, not a thing. But nevertheless, well, what I've got is a static image of Conway's game of life. This was an invention of John Horton Conway, who, by the way, died last month from COVID-19. So we're very sorry to have lost him, but a brilliant thinker. And he created this wonderfully enticing game that had very simple rules that drive very lifelike behavior. And it's a very thought-provoking kind of mechanism to think, to draw analogies between these kind of software-based automata and living things. When you look at, well, the reality is that we don't have a very good understanding of how biological life came around. There's this famous experiment, the Uller-Miller experiment from the 1930s, where Stanley Miller showed that looking at what we believe to be the atmospheric conditions of early Earth, that he was able to create a artificial environment where within the parameters of the early Earth conditions, he could show that amino acids would get synthesized. But amino acids are really a far cry from life. They're the building blocks of life, but they're not the self-replicating and self-sustaining molecular processes that form life. And we can only speculate at this point about how these self-sustaining processes, self-sustaining molecular processes came about. But my guess is that if we were to go back and be able to place ourselves and observe that process with biological life, we would have a lot of debates about whether these processes were really living or not. I mean, here's a bunch of molecules wiggling around, is that life? Nah, well, no, probably not, and people still have this debate. Viruses are often by biologists considered not to be alive, even though they have genetic material much like the rest of life, but they're considered not to be alive because they're unable to reproduce on their own. They need to hijack a bacterial cell or a eukaryotic cell, like a human cell, in order to be able to reproduce. And so many biologists consider them not to be living, but it's a very fuzzy boundary, because the fact is that there's actually no living thing that can reproduce without the help of other living things. Even a human needs the help of other living things. I mean, a woman has to stay alive for 9 months somehow in order to bear a child. And think about it. How do you stay alive without relying on other living things? I mean, you have to eat, for example, and that's what we eat. We eat other living things. And so every biological creature requires some help from its ecosystem in order to reproduce. So it's a very fuzzy boundary there. But my point is that if you were to look at the early emergence of life on the planet, it would probably be very debatable whether it really was a living thing. And I think that the same kind of debate is very legitimately applied to what we're seeing with technology today. So having said all that, in my book, I argue with myself. If I skip ahead to chapter 7, I then say, okay, well, wait a minute. Actually, particularly when you look at higher life forms like human beings, and when you look at intelligence, there's the gaps start to get pretty significant. And here I draw a lot from fairly recent work in psychology, and in particular the whole thesis of embodied cognition, which says that that the cognitive mind isn't something that resides inside the brain. It's the interaction of the brain with its environment. So that's a very subtle but extremely important distinction. So cognition is not what goes on inside the mechanisms of the brain. Cognition is the interaction between those mechanisms and the environment. Actually, one of the things that's so difficult about giving a talk like this is that the whole point of giving a talk like this is to connect with other human beings that I can only imagine are there. And I suspect that this would be impossible to do if I hadn't had some prior experience giving talks to actual human beings. So to quote Esther Tellin, who was one of the really key early forceful proponents of this embodied cognition idea, she said the mind simply does not exist as something decoupled from the body and the environment in which it resides. And so this says that if AIs are going to acquire something that closely resembles human cognition, they're going to need to have something that closely resembles a human body and have this ability to interact with their physical environment in much the way a human body interacts with its physical environment. And only that way are they going to, excuse me, are they going to be able to get something close to human cognition. Now, as they start to interact with their environment much more heavily, they may develop a cognitive mechanism by that interaction, but it's going to be a significantly different cognitive interaction because the body is going to be significantly different, and the interaction mechanisms between that cognitive entity and its environment are going to be significantly different. So these are, arguably unlikely to be in any way very closely resembling human cognition. There's been experimentation in robotics with embodied cognition in robots. So this is an image from a wonderful project led by Josh Bongard, where they created a robot that would learn to manipulate it to navigate by experimenting with its limbs. So it was not pre-programmed to walk with these 4 legs. And in fact, Bongard and his team showed that they could tear off one of these legs and the robot would stumble around for a while, but it would once again learn to walk with the 3 remaining legs. And they could also change the parameters of the legs. So they could put an extension on one of them to make it significantly longer than the other 3. And the robot would learn to navigate again through that modified body. So this is an approach that is starting to get these technological artifacts to have something more like an embodied cognitive self. Calling it cognitive is a bit of a stretch today, but even in biological entities, there's a whole range of cognition. I mean, you can have something as simple as a worm that has a neural system that has only a few hundred neurons, and yet it starts to exhibit certain behaviors that are cognition-like. So another topic that I address in my book is in getting more deeply at this question about what the differences are between human cognition and machine cognition and how machine cognition might evolve. The fact is that all of the machine mechanisms that we're building are digital. All of the AI technology today is digital. Well, there's some experimentation with non-digital technologies as well, but it's much less developed, shall we say. So the interesting question is, well, is human cognition digital? If it is, then in principle, if the technology advances enough, I should be able to upload my soul into a computer, because digital algorithmic processes in principle can be replicated on computers if you have enough resources, right? And so if my cognitive processes are fundamentally digital and algorithmic, then in principle, it should be possible for me to become immortal by transporting that digital algorithmic process into a computer. Similarly, teleportation should become possible. So the question is, are we really software and data? And does that lead us to the inevitable conclusion that AIs will eventually be able to completely replicate humans? Now, I argue in my book that this is actually not the case, probably. And that probably word is an important qualifier. I rely very heavily on a key result that was shown by Claude Shannon when he worked at Bell Labs in the 1940s. Claude Shannon showed that a noisy channel cannot convey more than a finite number of bits of information. Now, Shannon founded the field of information theory. And in his development of information theory, there's actually two very different kinds of information. Most people assume that information is digital because people talk about information technology, and all of the information that we have in information technology is digital. But actually, in Claude Shannon's information theory, information doesn't have to be digital. And in fact, he showed that this restriction that a noisy channel can only carry a finite number of bits of information actually means that an infinite amount of information is lost in any communication. An infinite amount of information lost in every communication, okay? So one of the interesting questions is whether human cognition actually has infinitely more information than can ever be conveyed out of it. So the argument is a bit nuanced, and you'll have to read my book to get my full defense of it. But I show, most importantly, that the hypothesis that we humans can be replicated by a digital algorithmic process cannot be construed as a scientific hypothesis because it is not falsifiable by experiment. And this follows directly from Shannon's result. So that means that if we ever develop a technology for uploading our souls, we will never know whether it works. Okay, and the only way you'd be able to tell whether it works would be to undergo the process yourself, and even then, you wouldn't be able to make the comparison between the before and after, so you still wouldn't know whether it had worked. So that argument that it's not falsifiable means ultimately that if you kind of believe in this singularity and believe that you can become immortal, you need to accept that this is a faith. And there's a long tradition in humanity of believing in the afterlife as a faith. So it's just a new version of that same story. Now, a lot of technologists say, wait a minute, that can't be right, because we actually have theorems that show that this should be possible, right? Didn't Alan Turing invent a universal machine? Well, many people do shorten universal Turing machine to just universal machine, but a universal Turing machine is not a universal machine. It can't do what my dishwasher does, for example. The fact is that Turing machines are algorithmic, digital, and terminating. And humans have only one of those three properties, terminating. We're not algorithmic. Our processes are not sequences of steps. We're not digital, or at least we can't be shown to be digital. Now you might say, all right, well, actually, maybe we are digital, right? Isn't the DNA digital? So there's the DNA fallacy. Human DNA encodes about 2 gigabytes of data. That's about 1,000 times less than what is on the laptop that I'm using to make this presentation. So it's not a lot of data, right? So is it really plausible that this 2 gigabytes of data encodes a human being? Let me point out that every human alive today is the endpoint of a continuous, unbroken biological process dating back 4 billion years. So me, my waving hand here, a biological process, is just a point in time on a biological process that started 4 billion years ago and has been uninterrupted that entire time. The amount of information that has flowed in that continuous flow is infinitely more than anything that can be conveyed in a noisy channel, because it doesn't have to be conveyed. It's actually carried in the thing in itself. So there's infinitely more information in that continual flow than there is in the DNA. So that makes it a little bit far-fetched that DNA alone will actually encode humanity. Well, what about cognition? We know that neurons fire discretely, so they must be digital, right? McCulloch and Pitts famously developed this perspective on neurons, showing that they fire discretely and that neurons combine to realize logic functions. Logic functions can be realized on other hardware. Hilary Putnam, the philosopher, used the term multiple realizability for this principle that you could perfectly replicate a process if it was a logical process on some other piece of hardware, and it would be indistinguishable from the original one. So in principle, if all of this is true, and we could just figure out all the connections between the neurons in the brain, we would be able to replicate these things on a digital machine. But that's proving to be a very, very far-fetched process. First of all, the human brain turns out to be far more complex than these Golgi-stained images seem to imply. It turns out that this kind of image, which is sort of the mental image that I had of what exists inside the brain, is profoundly misleading because a tiny subset of the neurons get stained in this. A more realistic picture has been constructed by Jeff Lichtman at Harvard, who has reconstructed three-dimensional models of tiny segments of mouse brains. And he actually coined the term connectomics and was pursuing this principle of that maybe being able to understand the interconnections between neurons would reveal something about brain function. And his research has led him to the conclusion, actually, that that's not the case, that we're not actually going to learn about brain function by looking at these connections between neurons, that the complexity and the intricacies in these connections is so vast that it's not going to reduce itself to these kinds of simple logical functions that McCulloch and Pitts were imagining. So my book also turns to questions of, well, all right, what happens when we get AIs that are driving cars and possibly running over pedestrians, and we have AIs that are making decisions about bank loans and so on. If we think of them as living things that we are actually co-evolving with, at some point it seems like we're likely going to reach a point where we're really going to need to hold them accountable for their actions. So that question of accountability is a very nuanced question, and it's a question that I confront in my book. This particular image is of an artwork that was created by three French guys, one of whom is Pierre Fautrel, who's the person in this image. And they downloaded a piece of software from Rabi Barat, who was a teenager who is now a student at Stanford. And Rabi Barat had created this program to use a technology developed by Ian Goodfellow called generative adversarial networks to synthesize artworks after extensive training from looking at existing artworks. And anyway, these three French guys, Obvious, created this artwork, which they called Portrait of Edmond de Bellamy, and they put it up for auction at Christie's, and it sold for some $430,000. And the idea was that it was the first AI-created artwork. So this directly, it created a lot of controversy, of course, because was it Rabi Barat's artwork, actually? Because it was kind of his software that created it. But my take on it is that these three guys created a piece of conceptual art. They created the concept of a first artwork created by an AI as a piece of conceptual art, and it's that piece of conceptual art that they sold. And you can only sell one of those, the first of these allegedly AI-created artworks. And it's a whole confrontation of this question of holding the machines accountable for their actions, right? They're basically throwing that in our face as a piece of conceptual artwork to think about. I think it's a brilliant commentary on a very prescient problem that we're actually all facing as technologists, because we're going to be having trouble with this accountability question. So we have to look more deeply at what we mean by accountability. And one of the things that I point out in my book is that in order to be held accountable for something, you have to be able to reason about causation, right? In order to be responsible for something having happened, you have to be able to reason about the fact that you caused this something to happen. Well, this question of causation turns out to be tremendously nuanced. This was really first pointed out famously by Bertrand Russell in 1913, who said, "The law of causality, I believe, is much like much that passes muster among philosophers, is a relic of a bygone era, surviving like the monarchy only because it is erroneously supposed to do no harm." So Bertrand Russell was basically throwing a bombshell into the scientific community here, saying that your whole premise that every physical thing is caused by a preceding physical thing, or physical process caused by a physical process, is bogus. That actually our best understanding of physics requires no such causation. And so this stimulated a whole line of work that has basically put forth the premise that the notion of causation is actually an evolved human cognitive concept and not a concept of about physics. So that's a very, very challenging philosophical perspective, but it has very practical consequences. And to understand these practical consequences, in my book, I turn to work by Judea Pearl, who's a Turing Award winner and the developer of Bayesian networks. But Pearl has shown that reasoning about causation fundamentally requires first-person subjective involvement. Subjective, okay? This is very problematic for people who hold as the ideal of scientific work always being objective. You always have to be able to step back, look objectively at something, and not be part of the experiment. And Pearl has shown very convincingly that as soon as you do that, you cannot reason about causation. It's fundamentally impossible to reason about causation without getting subjectively involved as a first person. And I actually developed that idea, and I tie it into the work of two other Turing Award winners, Robin Milner, and actually three other Turing Award winners, Robin Milner, Shafi Goldwasser, and Silvio Micali. The latter two with their development of zero-knowledge proofs, which is very closely related and also requires this first-person subjective involvement. And the whole point of this is that the first-person subjective involvement is actually a very powerful thing, and that we will never be able to hold machines accountable for anything until we can convince ourselves that they are able to actually have first-person subjective involvement. That's going to be the requirement. And the question remains, will the machines ever be able to develop a first-person subjective self? So the next chapter in the book is about pathologies. Things will go wrong. Of course, they will go wrong. But again, my book is not a doomsday book, but it talks about a few of the things that can go wrong. This is not a picture of the coronavirus spread, but it is a picture in my book. It's a picture of the WannaCry internet ransomware worm that spread through the internet in 2017. And it was quite a disastrous event. And in fact, it has tremendous analogies with viral pandemics. And in fact, the mechanisms that are used to counter it are in fact inoculations of antibodies, very analogous to the biological mechanisms that we use to control virus pandemics ultimately. So this chapter, the main point of this chapter is that many of the doomsday books think of the threat of technology almost as if it's an invasion of an alien species, and that we should do an H.G. Wells style war of the worlds and go to war with this invading species. And I say, no, it's more like a symbiotic relationship with another biological entity has gone wrong. So your gut bacteria, for example, has gone haywire and it's made you very sick. That's a pathology, and these kinds of things needed to be treated as pathologies, not as wars between invading species. I also make the claim that in this partnership between humans and machines, humans are the scarier part of the partnership. I'm going to skip this next section because I think I've gone on too long for an online talk, and skip right to the conclusion. So I apologize for skipping quickly through some slides, but I'd like to just entice you that coevolution, in fact, evolution, is a much more complex process than I thought when I started researching this book. I used to think that that mutations were very random, driven by alpha particles and chemical effects. But actually, I find they're much more complex. Biologists have learned they're much more complex. There's various mechanisms, like horizontal gene transfer, that are actually quite analogous to what a software programmer does. So here's a software programmer, and I coined the term horizontal code transfer. The software programmer is not starting with a blank slate and creating code from scratch. Nobody does that. Every piece of code that is written by a software programmer stitches together pieces of code from here and pieces of code from there to create a new piece of code. And in fact, viruses do this with the code in bacteria as well as in human cells. They mess with our DNA, and in fact, it's a fairly significant percentage of the human DNA is bacterial DNA that biologists understood to have been brought into the human germline relatively recently in our evolution by bacteria. So there's another very complex process called endosymbiosis that also has analogies with technology development, but I'm going to skip over that. People are very afraid that the machines are going to learn to write their own programs and are going to run away with themselves and outstrip humanity. There's an interesting mirror image effect that is already happening today, which is that computers are teaching humans how to program. When you use tools like Eclipse or Jupyter or GitHub or Stack Overflow or even Google Search, the machines are teaching you how to write your code. I find that my productivity as a programmer is orders of magnitude higher than it was 10 and 20 years ago. And that's because of these tools. These tools guide my programming and they show me how to do it. And that's an interesting process. And it's a feedback process, of course, because these themselves are all software tools. And they're software tools that are then further refined by the human beings who are using the software tools to further refine them. So that feedback loop where the human cognitive process of technology development is being affected by the technology, which is then affecting the technology, that feedback loop is subject to a mutation and natural selection kind of process. So the implications of all of this to regulation, I think, are fairly profound. So if you think of bad outcomes, right, under digital creationism, bad outcomes are the result of unethical actions by individuals, for example, by blindly following the profit motive with no concern for societal effects. Under coevolution, however, bad outcomes are the result of procreative prowess. Technologies that succeed are those that more effectively propagate. And that's a different mechanism. And arguably, you could say, well, you know, everyone likes to oversimplify things, right? It's the greed in Silicon Valley that leads to the destruction of democracy. You could also say that the machines are exploiting the human greed to procreate. Their own species is spreading because they're managing to get humans who are greedy to do the things that make their own species spread. So that's kind of a different twist on how this is coming about. And I think it suggests that regulating it is going to be much more challenging and that we're going to have to get a lot more sophisticated about how we talk about it. So the conclusion is that we nudge rather than control technology development. And we change as technology changes. A lot of the doomsday books put humans of today together with technology of 30 years from now. It won't be the humans of today with the technology of 30 years from now. It'll be the humans of 30 years from now with the technology of 30 years from now. And I have kids, and I know that they're already cognitively very different than I am, in large part because of their relationship with technology. And this change is accelerating. It's not slowing down. So it's only with a deeper understanding of these coevolutionary processes that we can have any hope of effective policies that ensure that technology will continue to serve humanity. So with that, thank you very much. I will stop sharing. And I think the plan is to open up the floor for questions if anyone is still awake. Okay, so I see a question from Oscar Pastor.
Yes, and the first one is from Monique Schnock.
Can you ask a question by Monique Schnock first?
Okay. So the question from Monique Schnock is, what would you consider the main key messages to give to our students? And what would you consider the best approach to teach them that message? Oh, I love that question. Thank you for that question. I think one thing that I would like to convey to our students is some humility. And that's actually hard for most computer science professors like me, because it's not, I think, in our nature. But the fact that we have less control than we think, I think, demands humility. And we should realize that, you know, that having that less control does not reduce our responsibility for what we do. And it increases the risks for what we do, right? So that means that we really have to step up our game. It's not, you know, a lot of people say, well, it's just a, you know, all we have to do is make sure we teach all our students ethics. And that presupposes that if every engineer acts ethically, you will not get bad outcomes. And I think that statement is patently false. We will get bad outcomes, even if every engineer acts ethically, because there's always going to be unintended consequences. And so humility combined with an understanding that we have responsibility is, I think, a very important message. The other thing I think is, I think it's important to not teach technology as a collection of facts, as if they were God-given reality, right? We have this tendency to think that, you know, the most wonderful contribution that a scientist can make is to discover something that previously existed. But that's not what technologists do. Technologists bring into existence things that didn't exist before. They don't discover things that previously existed. So this old-fashioned view that discovery is the ultimate objective, I think is just outdated. We're creating things that never before existed. We're not discovering things that previously existed. So under that perspective, it becomes very important to understand where the ideas came from. How did the ideas come about? So in my opinion, we should be teaching a lot more of where the ideas came from and who were the people who contributed to the development of the ideas, rather than just distilling the ideas to a bunch of mathematical formulas that we teach as if they were facts about the world.
Okay, there is a question I can find by Giancarlo Guisardi. Thanks a lot. Fascinating talk. So this is the feedback. Regarding the analogy with biological evolution, besides the Darwinian process, there are many elements of Lamarckian evolution in which people transplant ideas directly from one domain to another. Moreover, unlike Darwinian evolution, we have cases of backtracking with technology when old ideas are reintroduced in the arena. Could you please comment on that?
Yeah, another wonderful question. I actually talk about this in some depth in my book. I think biologists have come around and realized that Lamarck kind of got a bad name because he sort of got ridiculed for quite a long period of time with this sort of cartoon hypothesis that, well, you know, the way people would describe it is that, well, giraffes developed long necks because they were reaching for high leaves, and as they reached, their necks got longer, and those longer necks somehow got passed on to their offspring. And so that's what is called a Lamarckian mechanism for inheritance. And for, you know, until rather recently, it was widely ridiculed by evolutionary biologists. But evolutionary biologists have actually discovered in biology mechanisms that are distinctly Lamarckian, where, in fact, features that are developed by organisms during their lifetime do get passed on to their offspring. And we certainly see that in technology. I think technology develops and passes on to its offspring features that it acquires as it develops. So I think there's good analogies there, and I think in my book I talk about it in some depth.
Okay, I found the question by Oscar in the conversation. Amazing keynote. Thanks a lot, Edward. I want to ask you about the information systems connection. How can information systems engineering help to develop better machines, whatever better means in this context?
That's a difficult question. I think that in my book, I talk about the relationship between humans and computers today as being very asymmetric, okay? Even though we've had spectacular success with AI in the last 10 years, I would say the machines are, in many dimensions, much more primitive organisms than human beings are. And there's a huge asymmetry there. I mean, in other respects, humans are much more primitive than the machines, right? I mean, Google can search through vastly more data than I can, for example. So there's very complementary effects there. But we have those kinds of asymmetries in biological relationships as well. So we have, for example, our gut bacteria, which are, you know, very, very much a part of the human body. And they're bacterial cells. They have a completely different DNA than the eukaryotic cells that form the better part of our body. But they are arguably very much part of our body. And I think that our relationship with technology is starting to become more like that kind of symbiosis, where I guess biologists would call it an endosymbiosis, where neither partner in the symbiosis can live without the other. And I suggest the thought experiment in the book. What do you think would happen to humanity if right now we were to turn off all the computers on the planet and leave them off? And I think that if you think it through, you realize that this would be much more devastating than the coronavirus. It would lead to probably billions of deaths, not hundreds of thousands. And it would lead to mass starvation, and we can't support 7.7 billion people on the planet and feed them without the technology that we're using today to run our economic systems and our transportation systems and so forth. So we're already in this very strongly mutually dependent symbiotic relationship with technology. And, you know, people who say, well, they reassure themselves that we'll just, you know, if the AIs start to get dangerous, we'll just pull the plug. We're not going to be able to pull the plug. In fact, we already can't, right? I mean, think about what would happen today if you pulled the plug on all the AIs that are doing all the fraud detection in our financial systems, that are doing all the spam filtering in our email systems. Our entire communication network would break down. Our entire financial system would come apart if we pull the plugs on those AIs. We're already at the point where we can't pull the plug on the AIs. So we're past that point.
Okay, thank you. I think that was the last question I could spot from the people in the audience. I had a question myself. Actually, I had several, but I'm going to merge them in one. It's quite related actually to Oscar's question. I think at the beginning of your talk, you talk about a Darwinist approach of software engineering. And this Darwinist approach of software engineering, somehow, if we follow your thought, it implies somehow to better address the question of the human in the loop when we design software systems, software ecosystems, or human socio-technical systems. This can be this is what we try to do when we design system, when we try to understand what are who are the stakeholders, what are the characteristics of the stakeholders, the relationship with the wider environment, their goals, and how their problems, and how the systems we design would help them better achieve their goals. But somehow it appears also that we are missing a lot of information about these people who are in the loop. And we can observe at the same time that unicorns are better than us in collecting information about the human in the loop. They collect a lot of data, mainly for marketing purpose, about their users. And in fact, the question could be, why not use all this data as to introduce in the feedback loop, which seems to be necessary in the software design, and go more in the sense of a kind of radically new software development life cycle that would really integrate what some people would call crowd innovation, but not really crowd innovation. In influence from the user by design.
Yeah.
How about that? Does it make sense? Is it consistent with what you're saying?
I think we've already gone partway down that path, and I think there's a lot of room for innovation, and this is really the right community to do it. But let me just talk about the migration from waterfall models to agile models for software development. Right. I mean, what's the difference there, right? In the waterfall model, there was this ideal that you could have kind of a specification ahead of time before you really started doing any detailed design, and then you do the detailed design on the basis of the specification. But people who develop software know that that's not the way software gets developed, and it's really pretty impossible to develop software that way because the specification is always going to be so absurdly wrong if you develop a completely open loop. The process has to be much more iterative. The process is an iterative process of trying out a mutation and seeing if it works. And then a lot of them fail, and you leave them by the wayside, and you modify your mutation, and you go through this iterative process. And that iterative process is very much analogous to a biological evolutionary process. And again, it doesn't, I used to think that biological evolutionary processes were just purely random mutations, but they're not, right? If you construct the statistical model of how bacteria would evolve with random mutations of the DNA, then we wouldn't have antibiotic-resistant bacteria. There hasn't been enough time for the statistics to be able to support the development of antibiotic-resistant bacteria by those kinds of purely random mechanisms. So this is why biologists started searching for and finding other mechanisms where there were agents involved in this mutation, viruses in particular, which were really triggering a much more rapid change in the DNA of the bacterial molecules and creating these, bacterial systems, and creating these feedback loops that would then accelerate the evolutionary process very dramatically. So over very short periods of time, you could get quite an advance in the genetic material in a colony of bacteria. Same thing happens in software, right? You get a team of people working on an agile process, and a lot of random stuff gets tried and discarded, and some of the random stuff works, and then the agency of the participants affects the random stuff, of course. But it's so it's a partly random process, partly agency-driven process, but very iterative process.
Okay, thank you, Edward. Let me try something.
Okay. Thank you very much.
Yeah, we missed that. And unfortunately, that's something that neither Zoom nor Whova will provide. I think everybody here from their warming messages in Zoom accompany me in congratulation and thanking you for this very enlightening talk. That starts the conference very, very well.
It's really my pleasure, and I wish that I could go now and have a glass of wine with you all and continue the discussion, but hopefully.
Oh yeah, I hope it's very, very, very soon.